All right, okay. So we're in 4.2 here. We're doing more probability. Chapter 4 is all about probability. We're doing a little bit more probability. So when randomly selecting an adult, A denotes the event of selecting someone with blue eyes. What do P of A and P of A bar mean? So just getting into some of the so basically this section, well, I'll write up later what it's about. So it's saying A is somebody has blue eyes. So what's P of A then? Well, there's P of A and there's P of A bar. So it's the bar on it that is the not. Remember that from earlier? So this would mean, so P of A, the P stands for probability. So that's the probability of A, and A is what? Blue eyes. So that's the probability of selecting somebody with blue eyes. And PA bar is going to be the probability of somebody that does not have blue eyes. This making sense so far? So the P just stands for probability, like the chance. We don't know what those are yet, but they're just getting us used to the language, the lingo. So P of A is the probability of somebody with blue eyes, because they said A, they said up here, A denotes blue eyes. And A bar is not blue eyes, any other color than blue on that. So if we come on down to this, what are we going to get? Which one of those is it? Is it this one? Event of selecting with blue eyes, yeah. And the next one would be this one. Selective adult who does not have blue eyes. Yeah, there we go.
Event or probability? Because I did probability and it said it was right.
Oh, you're right. So, thank you. I didn't even notice that little word. They're tricking me. It's probability. Yeah, it's probability, not event. Yeah, thank you. Yeah, it's probability. The P is for probability. Good? We good? All right, let's keep moving. Number 2, Research Center poll shows that 85% of people believe that it is morally wrong to not report all income on tax returns. Timely time of the year, huh? Maybe, yeah. Sorry, I feel like making jokes about taxes. I shouldn't. All right. What is the probability? What is the probability that someone does not have this belief? Okay. So if 85% of the people feel that way, then what's the chance that someone does not feel that way? So that's just like, if there's 85% chance of rain, what's the chance it's not going to rain? 15, huh? It's the rest. Yeah, it's all you got to do is subtract from 100. Does that make sense? Whenever you do the opposite, whoops, that's supposed to be 100. So 100% minus 85 is 15. So if 85% of the people think it's wrong, then 15% don't. Is that good? On that, making sense? On that? All right. So we'll move on. Number 3. Find the indicated. Okay. A certain group of women have 0.37% rate of red-green color blindness. Who has color blindness more? Yeah, men a lot more, huh? Like way more. I don't know what the numbers are, but yeah, way more. So very rare for women to be colorblind. 0.37%, let's say. Now notice that's 0.37, huh? Percent. It's not just 0.37. I said that backwards. Let me write that clearly. So in other words, that's 0.37%, which means it's what decimal? 0037. I want to make sure you're clear on that. Right? It's lower than 1%, isn't it? See how that works? Got to watch out for that. In other words, it's not 37%. It's kind of like the 99-cent thing we were talking about. Right? They have a decimal there. So that's less than 1%, isn't it? So, which is the same as 0.0037. Watch out. They're being tricky with the decimal there. So anyway, it's super small. Super, super, super small. So what's the probability that you're going to pick a woman that does not have the red-green color blindness? So basically, these questions are opposites. Do you see what we're doing there? Maybe I should write that out more clearly for you. Whenever you do the opposite, so the opposite, it's 1 minus the regular, isn't it? Or 100% minus the regular. Yeah, let me write that out for you. So whenever you're doing the opposite, that's what we're doing in these last 2 or 3 questions. It's always 1 minus the regular, and 1 is the same, 1 decimal, 1.0 decimal is the same as 100%. Are you comfortable with that? They're going to interchange those back and forth. So I want to make sure you're okay with that. So 1.0 decimal. So if they give it to you in decimals, just use 1.0. If they give it to you in percentages, just subtract from 100. Both are good. Both are right. Am I making sense?
Do you have to put the percentage sign?
I don't know. Let's see what they want. They said type an integer or decimal. So they don't want the percentage, I guess. Yeah. So if they don't put a percentage there, then they don't want percentage. So they don't want percentage on this one. So that's why, so it is good that I changed it here to decimal. And so I'm going to do the decimal 1.0 minus 0.0037. So that would be the chance of the opposite. And that'll be, what is that, 0.9963? 0.9, so that's our answer. 0.9963. Yeah. Yeah, Sean's question is good. Everybody see that? Yeah, so when they don't put a percentage there, then they just want a decimal answer on that. So I just changed it to decimal. Whenever you go from percentage decimal, it had to go back 2 places, right? You good there? That's why there's 2 zeros in the percentage symbol. It's just saying you got to move 2 places on that. So I moved it back 2 places. That good? Making sense on that? All right, yeah, so watch out for that. That can mess you up. So opposite is always 1 minus or 100% minus. All right, let's go on to number 4. So when a man observed a sobriety checkpoint conducted by the police department, he saw 673 drivers screened, 3 were arrested for driving intoxicated. Based on the results, we can estimate that P of W is 0.00446, where W denotes the event of screening a driver and getting someone who's intoxicated. What does P of W bar denote, and what is its value? Okay. All right, so a lot of words, huh? A lot of words on all these. So what they're talking about is they're doing the opposite again. So remember, W bar is the opposite of W. W bar is the opposite of W. And so they're telling me the probability of W right there. So the probability of W is 0.00446. So how am I going to find the probability of W bar?
Negative? To make that 100.
Well, I think we could just keep it as a decimal. I think they just want a decimal answer, don't they?
1.0.
Yeah. So just take, does it make sense? Just take 1.0 minus it. Yeah, so it'd be 0.99554. Is that making sense? Should I slow down there for a minute? So on these last 3 questions, it's always the same thing. They're asking me for the opposite. So they put the bar over it. That means the opposite. And the way you get it is 1 minus in decimals. Is that good? And then they want some words. And what's it going to be? What is the opposite of, what was W? Come back up here. W denotes a driver getting screened and intoxicated and getting arrested. So then, finally here she is not into, C. Yeah, so it'd be C, exactly. Because C, finding here she is not intoxicated. That would be the opposite of the W. How are we doing? Is this making sense for you? So these last 3, it's all about opposite. It's all about opposite, and that's always 1 minus the decimal on that. That good? Questions I can answer? Okay. Let's move ahead. So, number 5. Okay, they're going to give us these tables now about drive-through restaurants and the percentage of things. So, drive-through restaurant A got 313 accurate, 30 not accurate, B, C, and D. If one order is selected, like at random, find the probability of getting food that is not from restaurant A. Food that is not from restaurant A. Okay, so how are we going to do that?
You add everything up?
Yeah, good. Ken's right on the money. To see what's going on there, you have to, because remember, probability, and what are we doing? We're doing the probability not A, not from A. So probability of not A is going to be whatever the number that are not A over the total, huh? Remember how probability always has total on the bottom? So we just need to find the number in that table that are not restaurant A. It doesn't matter whether they're accurate or not accurate. That's not important on this question. We'll take them both. We take them all on that. Is that making sense? So what would the total? So if you add all those up in your calculator, if you add this and this and this and this and get the total. Somebody got that? I'll do it too. 7? Did you guys, anybody get that? From adding those all up?
Yeah.
Okay, good. And then the number not A. What is the number that are not from restaurant A?
343.
That'd be this, and that, huh? All the B, the C, and the D, those would all be not from restaurant A?
So 1,097 minus 313 and 30?
Yeah, minus 313. Yeah, good idea. Yeah, the easy way, I like your plan. Yeah, the easy way would be just to take the total and just subtract the two A ones, huh? I like that. I got 754. How are we doing? Is this making sense with what's happening there? So they're asking for the probability that they're not restaurant A. So I added up all these, 754 over the total. And then you just divide on your calculator. They want it rounded to 3 decimal places. So 3 decimal places. So I'm getting point 687 rounded to 3 decimal places. So that's the answer. So that means if you grab one at random, the chance they're not from restaurant A is 0.687. In other words, that's 68.7%, isn't it? Questions on that? It says, not accurate. Not accurate, yeah. So number 6, they want, we're using this table, and we're saying not accurate. All right, so we have to have the total on the bottom, and not accurate is what they're asking us to find. So that'll be on the top. So the total would just be adding all those up. Somebody got that total? What is it? 1,279. Is that good? A couple people getting that?
No, I'm sorry, no, 1,102 for the total.
Oh, okay. 1,102? 1,102, like that? Other people getting that number?
Yeah.
Okay, good. Looks good. So that's the total of all those added up. And then how many are the not accurate? So that'd be these bottom ones, huh?
141.
Is that what it is? 141? Good. And then just divide those. So 141 divided by 1102. And you get, I'm getting, what do they want, 3 decimal places? 0.1279. So that would round to 0.128, huh? 3 places. 0.128. Is that good?
For 7, I don't know exactly what it asking. Because it says, find the probability of getting an order from restaurant A or an order that is accurate.
Yeah, I'll show you. We'll go there. Are we good on 6? It's making sense. Yeah, they get a little more tricky with their language. Let's look at 7. So they give us another table, but yeah, look at the question. It is more tricky. Restaurant A or accurate. So like if you said, I'm going to grab one of these at random. What's the chance I'm going to get one from restaurant that's either from restaurant A or it's accurate? So basically, A or accurate on the top, bottom's total like usual. Okay, now how do I do A or accurate? How's that? Well, these ones would be A. And which other ones are accurate? These ones. That would be the top. All those. See how that's all those ones I've circled are either restaurant A or they're accurate. Because the top row is accurate.
Okay, so then we just add this up.
Just add them up. Yeah, so those will just all add up for the numerator. And the denominator is still the total. Does that make sense? So I'll move on. If you're good with that, I'll move on. So you just do the adding. Is that okay? Do you want me to do that one out? So if we added up the top there, so 3, 2, 3. $994, and the bottom is whatever the total is. I think it's 1092. That's what I'm getting anyway. Did anybody else get those numbers? Yeah, you got the same ones?
I had a different problem, but I get the same number.
That's funny. And when I divide, I get, what?
She said and, I said or.
910. 0.910. How are we doing? Is that making sense? Are we getting those answers? You see how I did that? I just added those up. Good. Okay, so let's keep going. Now they have an extra question for us here, and that is, are the events restaurant A and accurate disjoint? So what does that mean? Disjoint events cannot both happen. That'd be like rain and no rain, or, the things that can't both happen. Today we had, I guess that's not the best example. I guess you could have times of, but, of that. But, if you said, hey, the team won and they didn't win the same game, that can't happen. That's disjoint. You either win or you lose. Right, but you can't win and lose still.
Okay.
So I know you're soccer. There's a lot of tying in soccer, isn't there? I know. So does that make sense? So disjoint. So that'd be a good word to put on your 3x5 card. And we're a ways out. I'll remind you as we get close to the second exam and we go over the practice exam. At that time, I'll remind you. But yeah, disjoint means they can't both happen at the same time. So the question is, are these events disjoint or not? Restaurant A, accurate. Could those both happen at the same time? Could you have a meal at restaurant A and it be accurate?
Yeah.
Well, yeah. In fact, 323 people had that experience. Right? They had a restaurant A accurate order. So these events are not disjoint. They can both happen at the same time. Does that make sense? I know we're using all these negative opposite words. It gets a little confusing. So again, disjoint means they're like, think about it like disconnected. Or if something's disconnected, it's not working together. These do work together, don't they? So we would say these events are not disjoint because it is possible to receive an accurate order from A. It is possible to do both. Is that making sense? So again, disjoint means like if you have a joint that's disconnected or something, they're not together. They're not together. Well, these could be together. You could have an order that's accurate from restaurant A. So they're going to ask you about the disjoint thing on all the rest of the questions. Is that making sense? On that, feel free to speak up if you want to talk more about that. So this is going to be the same kind of thing. Maybe let's just circle what we need to circle. Let's see, what do they ask? They're saying restaurant C or not accurate. So can you circle in the table? So restaurant C or not accurate. Restaurant C or not accurate. So restaurant C would be these. And then not accurate would be what, the bottom? So it'd be this. Where I'll do a different color. It would be this and that, huh? Is that good? Restaurant C and then the not accurate. We good like that? And so then you would just put that over the total. Now here comes the next question about the disjoint thing. They're going to basically say, hey, are those things disjoint? A restaurant C and inaccurate, not accurate, are those disjoint? Are those disjoint? What do you think? So now, are those disconnected so they could never both happen at the same time? No, you can have that happen at the same time, huh? We good there? So they're not disjoint. You could have restaurant C and an inaccurate order from restaurant C. In fact, 33 people had that, huh? An inaccurate order from restaurant C. So they're not. It's not inaccurate. Yeah, I'm sorry, it's not disjoint. Not disjoint. All right, I'm going to move on. Let me know if you want me to slow down and talk more about it. Number 9 is the same thing. Well, no, we could do it real quick. Restaurant A or restaurant D. Oh, no, or not accurate. So that'd be all the restaurant A, all the restaurant D, and or not accurate. So that would be what? This and this? All those added up, huh? Just a whole bunch of them. We good to there? Question 10. Question 10 is going to be your favorite question. I'm betting. I'm guessing. Is it not? I think it will be, because I'm going to do this. I realized later, like tonight, a couple hours ago, that it was trickier than I thought. And I just skip it. Don't worry about it. If I could remove it, I would. It won't let me remove homework once people started working on it. It won't let me change it. So don't worry about it. I promise to not hold it against you on your grade in the end. It won't let me just pull it off, or I would. So just forget about number 10. Don't worry about it. There's like a trick thing you have to do. I don't want to talk about it. It's not worth it. It's complex, and I tried to avoid those particular type when I looked through. It's like some little weird thing that's of no benefit to us. If we were doing like a whole class on probability, then yeah, it's like a trickier probability thing. We're just trying to get a little bit so we can do stats well. So forget about number 10. It will bring your homework score down, but I promise to not hold it against you. I wish I could remove it, but it won't let me.
Can you just give us the right answer so we can put it in?
It changes the numbers for everybody, I think. Yeah. So, yeah. So don't worry about it at all. Just skip number 10. So, yeah, maybe I'll write that on the board too. Move on. So, number 11. Use the following results from a test for marijuana use, which was provided by a certain drug testing company. It's funny, this is like an old thing that I don't think that would happen anymore, because it's illegal now. Anyway, this must be an older problem. So, among 145 subjects with positive test results, there are 25 false positive results. Among 150 negative, there are 3 false negative. So how many subjects, what's the total number of subjects in the study? So it's making us read all those words real careful.
295.
Is that what it is? So how are you coming up with that, Ken?
145. 145 subjects were positive and 150 were negative.
So 145 positive, yeah. You know what? It might be nice is to make a table. I wonder how could I do that? See, among 145 positive. So this would be positive, negative. So tested positive or negative. And they use or they do not use marijuana, right? That would be what we're looking at. So let's see. It says 145 subjects were positive, but 25 were false. So
I just put the 45 on the positive.
25 and 120.
No,
I think, right?
no, because the whole total is 145.
Right. So that would be what the positive adds up to be.
Mm-hmm.
Does that make sense how I'm coming up with that? So what I'm doing there, let me slow down and help. It said 145 got positive. So you can put that number down first if you want. 145 tested positive. You know, because some of those that test positive really are using and some are not. So 145 tested positive, but 25 false positive. So 25 really don't use, huh? And then if you subtract that, you'll get this. On that, just take 145 minus 25, you get the 120. So I'm coming up with that. Okay, can you do the other side? So you try the other side. Let me, that'll...
We were false positives from that?
Yeah, because I knew exactly. Because there's 145 total that were positive, but they told me 25 were false, so they really weren't users.
Yeah, that didn't work for me.
You mean you have different numbers, or?
No, yeah, I have different numbers, but I typed it, I had 145 were positive and 21 false positive results, and I typed in 124.
I haven't answered the actual questions yet.
Okay.
Yeah, let me see. I'm not sure what they will come out to be. Let me do the other part, then we'll answer the questions, yeah. So next, 150 negative. So that would be the total down here, right? 150 negative. It says 3 false negative. So where did the 3 false negatives go?
They use.
Yeah, because they actually use, even though they got a negative result. So they're false. So they go right there, right? And then subtract 150 minus 3. This must be 147. Does that make sense how I'm doing that?
Yeah.
Is that okay? See how the table works? So that means there's 3 people that got a negative result, but they actually use. So that was a false negative. And 147 people don't use, and it said they don't use. They got a negative result for the 150 total negatives. And then the other. So now we're ready for their questions. Here come the questions. The total number of subjects in the study. So how do we figure out the total number of subjects in the study? You add them all up, or you could just add up these bottom 2 numbers because these are the totals of the 2 columns, huh? That's what Ken was doing, I think. Right? That'd be the quick way to do that. Just add those up. So that's going to be 295 if you add those up on that. So I'll just put that over here. So 145 plus 150 is 295. 295. So that's the total number of subjects in the study, 295. And then how many subjects did not use marijuana? Did not use marijuana. So how we figure that out?
150 minus 3.
We need to add those 2 up, don't we? Those are both the groups that don't use. Some tested positive, some negative, but they're all people that do not use, huh? So that would be the 25 plus the 147, whatever that is. 172, thank you. 172. This table making sense? How that works? And see, what's the probability that a random selected subject did not use marijuana? So if you're to grab somebody at random out of all these people, what's the chance that you would get somebody that did not use?
About 172 divided by 295.
Yeah, right, because did not use, so it's always, whatever you want, in this case, did not use over total, huh? Yeah, and how many did not use? Well, we just figured that out. Right here, it's the 25 plus 147, huh? Am I writing too small? Can you read that? So it's going to be the 25 plus 147 over the total, and the total was 295. So this is 172 over 295. I'm getting 0.583. They want a decimal for 3 places. Yeah, 3 places. 0.583. So that means 58% of the people did not use that were being tested. Just over half. How are we doing on that? How about we try number 12? Alston, you try it. See if it works. On that, I think that's always probably the best way. So let's try number 12. 12 looks like it might be different. I don't know. Let's see. So, wait, what did we just did 11? So it's another marijuana one.
It's the same,
Is it exactly the same?
like same style.
Yeah. Maybe I want to get through to 17, and I want to give a couple minutes to answer test questions at the end. So maybe I'll move on. Any other questions I can answer, though, on 11? Before I move on too quick, you okay with how I made that table? So whenever we have things with false positives and false negatives, it's always good to make a table like this, where you have positive and negative, and then, they use or they do not use. And then just fill in the different things. And is that good? That okay? And so 12 is the same, I'm assuming. It looks exactly the same. 30 false positive, 160 negative. Yeah, same exact thing. So I'll go on to 13. 13, the principle of redundancy. Oh yeah, this is valuable. So suppose an alarm clock has a 17.8% daily failure rate. Is that how your alarm clock works? 17.8% daily failure rate. So, what is the probability that a student's alarm clock will not work on the morning of an important final exam? I'm going to tell you. I've done it. Been there, done that. 17.8%. So let's say the alarm has a 17.8% failure rate. So what's the probability it will not work on the morning of an important final exam? So failure rate means the percent chance it's going to fail, huh? 17.8% of the time it fails. So what's the chance that it will not work? Well, 17.8%. Do they want percent? Oh, they want decimal, huh? So I've got to change the 17.8% to a decimal. So when I change that to a decimal, it's 0.178. It goes back 2 places, doesn't it? So this would be 0.178. That's the chance it's going to fail. Okay. So part B. So what could you do? If the student has 2 such alarm clocks, what's the probability they both fail? All right, so here's a new question. We're going to do something new here. So we're shifting gear for 13, 14, 15, 16, 17. These last ones, we're going to answer all these same kinds of questions. And that's basically when you put 2 things together, how does the probability work? And the answer is you multiply them. That's what you actually do. So when they're saying, okay, there's a 0.178 chance of failure. So if you have 2 alarm clocks, what's the chance they're both going to fail? They'll both not go off. Pretty low, huh? That would help, wouldn't it? Have you had 2 not go
I
off?
always said 2 alarms, like 1 for 5 and then 1 for 5:10.
Well, you get up too early, Eddie. That's the problem. I can't, I'm just wimpy compared to you. I can't get up at those hours. So 0.178 times 0.178. So you actually multiply those together. That's how you do the and thing there. Is that making sense? So the chance, the first rule, so and means multiply. That's the main principle I want you to see. Remember earlier we were doing or? Let me write that. Or means add. That's the title of this section. It's multiplying and adding when you do it. So remember those ones we did a few minutes ago when they said restaurant A or got the order wrong? Remember we would always add those up? So or always means you add. If it's this or that, you add. And means you multiply. So if you're saying what's the chance the alarm is going to fail, the first one's going to fail, and the second one's going to fail, you would multiply that together. For both fail, and. So it's not or, huh? They're not asking us or. Do you see that they're asking us and? They're saying the first fails and the second fails. So if you multiply that together, I have no idea. That I'm getting 0.0316, so 0.031684. So there it is. They want you to round to 5 places. 1, 2, 3, 4, 5 to there. So it's 0.03168. So notice it's a much smaller percentage chance, isn't it? See how it got much smaller? Right? So if the chance of one alarm clock failing is basically 17%, the chance of both failing is just 3%. It goes way down. That's what they do, to increase security. We're going to get some other security things. Is they'll just put several things in a row. That's like what a hospital does. We'll get to a hospital problem where they'll have 3 backup generators because the chance that all 3 will fail is super low because you multiply those together. And that feels right, doesn't it? The chance that both alarms would not go off is going to be really low. And it is. Okay, and then C. What if the probability, if they use 3 of them? What if they use 3 of them? Yeah, just multiply that together 3 times. So for part C, it would be the 0.178 times 0.178 times 0.178. It's going to be super small, huh? I'm getting 0.005639. How far do they want? 5 places. 3, 4. So it'd be so to round. So remember how are you guys okay with the rounding? So to round, you just circle the place they want you to stop in. They said 5 places, right? Yeah, 5 places. So 1, 2, 3, 4. There, this one's in the 5th place. Then you just look 1 to the right. 4 or more goes. 5 or more goes up. So 564. 0.00564. 0.00564. So now it's super low. That's under 1%, right? If you move that decimal 2 places, that's 0.5%. That's 0.5%. Super low chance that all 3 alarms won't go off. Less than a 1% chance. About a 0.5% chance. Are we good there? So for and, you just keep multiplying together. That's really the main idea of this section. Or you add and you multiply. Question D. Do the second and third alarm clocks result in greatly improved reliability? Yeah, for sure. They do, huh? Putting extra ones really do. We'll say yes. Is it that one?
Yeah.
Because total malfunction would not be impossible, but it would be unlikely. Yeah, it'd be very unlikely. That's the answer. Is that good? The others are going to be just like it. We'll do a couple. Then maybe I'll leave a few minutes so I can answer your test questions. Questions on that one? Is that good?
We'll do 14.
Yeah, is 14 good? Let's try that one. Oh, hospital. There's a hospital problem. Okay. Emergency backup generators fail 32% of the time. That's pretty bad. So if they have 2 backup generators, find the probability that both fail. So during a power outage, when you need the backup generators to kick in, what's the chance they're both going to fail if they each have a 32% chance of failing?
10, 24.
Is that what you got? How'd you get that, Ken?
I just multiplied
Perfect. 0.32 times 0.32? Yeah. Is that good? Is that making sense? So and you just multiply them together again? Or you would add. So I'm getting, 0.1024, is that what you said?
Yeah.
0.1024, which is like 10%, huh? So it went down from 32% to 10%. Very low chance of fit. Now, B, find the probability of having a word generator then prior to... Okay. Is that probability high enough for the hospital? What? What did they say? Find the probability of having a work generator in the event of a power outage. Oh, that's... Yeah, so what's the chance... And they say, assume...
Yeah, that one's hard. Percent.
Oh. Yeah, it's weird words. What they're saying is, what's the chance it's going to work? What's the chance it's actually going to work? How would we answer that?
So 0.99 times by itself?
Yeah, exactly. Well, it's going to be, because this is the chance it's going to fail, right? And so work is the opposite of failing. So how do we do opposite? Remember how we always do opposite? 1 minus. Remember, like if the chance of rain is 80%, the opposite chance it won't rain is 20%. That's 100% minus. So whenever, so opposite, work is the opposite of fail, huh? The chance the generator will work is the opposite of the chance it's going to fail. So that's going to be 1 minus the fail chance. That's 1 minus the 0.1024, which will be 0.8976. Yeah. 0.8976. That makes sense what we did there? So whenever they ask you an opposite question, you always do 1 minus. So the chance it's going to work is the opposite of the chance it's going to fail. 1 minus on that. So, all right, so is that good? Is that, no, they need it to fail less than 1% of the time. We got it failing 10% of the time, huh? That's 10% basically. So this is not a good plan. So what's their question? Is that high enough? No. That's not high enough for the hospital. They can't have it failing 10% of the time. No, it's not high enough because both generators fail about... so basically, I'm going to take the fail answer here. I'm going to take this fail answer, right? This is the fail answer. And change it to percentage. You see how they have a percent? That's how you know you're supposed to go to percent. They put a percent symbol there. So I'm going to say no, because both generators together fail. And how do you turn that decimal into percent? 2 places, yeah. 2 places to the right. So that'll be 10.24% of the time. Oh, it says whole number. I didn't read that. So what would be the nearest whole number? Just 10%. So they fail about 10% of the time. That's not good. It's supposed to be less than 1%. So that's not good. We good there? How are we doing? Have we done them all? I mean, I know there's 3 more, but are they the same?
No, that one's hard too.
Is it? Yeah, there's some tricky ones here, huh? All right, among 6,555 cases of heart pacemaker malfunctions, 378 were found to be caused by firmware, which is software programmed into the device. Firmware is tested in 3 different pacemakers randomly selected from the batch, and the entire batch is accepted if there are no failures. What is the probability that the firmware will be accepted? Okay, that's a lot of fancy words. In other words, one of the main uses for an important use for statistics, I don't know if it's a main use, but is testing. Like, how do companies test their products? So if you're producing something on the assembly line, something important like pacemakers, you don't want to be a company that produces a lot of bad ones. Obviously, the doctors aren't going to order your products anymore, and people are going to be harmed. So how they have to test things. Now, a lot of times they don't have time to test every single one. When they're producing millions and millions of things on an assembly line, that would be best, obviously, if they just checked every single one. But the reality, and probably for something like pacemakers they do, I mean, that's important. But not for everything. Not everything made is tested every single item. Instead, what they do is they make up some plan, like we'll just test every 10th one, or we'll take a batch of 100 and we'll test 3 out of every 100, or whatever. They make up some kind of plan, and if they look at a group of 100, they test 3 and one of them's bad, then they send the whole batch back, or something. They make up various plans. Well, they do that with statistics knowledge, because what they want to know is, what's the chance that our plan's going to let bad stuff through? Or, put more clearly, what percentage, because bad stuff will get through, but what percentage of the time will bad stuff get through? And how much can we afford as a company to let bad stuff get through? And we have to balance that with how much we have to pay people to do all this testing. The more we test, the less bad stuff gets through, but the less we test, the more bad stuff gets through. And they kind of balance this out. They need people to do statistics and tell them what the likelihood is for all this. All right, so with all that said, that's what's going on in this problem. So here's their plan. I think they have pretty much a terrible plan. They're going to basically take 6,555 pacemakers, and they're going to just test 3 of them.
Dang.
And if those 3 are good, the entire batch is accepted.
How do they test them though? Like monkeys?
I don't know how they test it, but I think it's electronically. But does that make sense what their plan is?
Yeah.
They're going to grab 6,555, and they're going to test 3, randomly selected, and if those are good, the entire batch is declared good. So the question put to us then is this procedure likely to result in a batch being accepted? Now, we already know this batch has 378 bad ones, right? See what they're saying right there? 378 are bad firmware. So let me ask you, if 378 out of 6,555, that's how many are bad out of the total, right? In that batch of 6,555, 378 are bad. So if 378 are bad out of that total, what is that? What portion is that? What's the probability of that? I'm getting, 0.057669. Okay, now what that is, hold on for a second, that's the chance of getting one bad one. Do you realize? Now, if somebody said, hey, just reach into that batch and grab one, what's the chance you're going to get a bad one? That'd be that. Right, that's right, because you just reach in, you grab, there's 378 bad ones out of 6,555 total. If you just grab one, that's the chance you're going to get a bad one, huh? They're asking, what's the chance you get 3 good ones? I'm doing the wrong thing. We want 3 good ones in a row, don't we? So instead of putting the bad on the top, let's put the good. So how many good ones are there? Well, yeah, just subtract them, huh? It's 6,555 minus 378. If you subtract that, what is it?
6177.
Thank you, 6177. So there's 6177 good ones. So let's divide that now on our calculator. 6177 divided by
1.423.
yeah, 0.9.
423340961.
Yeah. So that's the chance of getting a good one, right? So if you reach into this batch that has 378 bad ones out of 6,555, chance you'll get a good one is that. And they're saying, what's the chance you're going to get 3 good ones in a row? Because that's when you'll accept the whole batch. Right? If the inspector just grabs 3 and they're good, then he's going to say, let the whole batch go. Just put them in people, whatever. Right? That's what he's going to do. This is a terrible plan, obviously. So what's the chance he's going to get 3 good ones in a row? That's and, isn't it? Good one, and good one, and good one. So it's another and question. You just take this and multiply it by itself 3 times. You know the easy button to do that on your calculator? There's a third power button. To the third power. Because that'll mean times itself 3 times. You'll have, on your graphing calculator, you'll have a up arrow. Do you see that up arrow? So if you just go up, if you just have this answer on your screen, if you just literally hit up arrow 3 and then hit enter. Up arrow is on the right side. It's over on the right side there.
Oh.
You see that? So first off, just divide these on your calculator, get that answer, and then literally just hit up arrow 3. That means to the third power. Means times itself 3 times. And hit enter. See that up arrow on the right side?
Yeah.
To upper right? And let me see what we get. Up arrow 3, I'm getting 0.8367. Y'all getting that?
Yeah.
That's the chance of getting 3 good ones in a row. I don't know how many, 3 decimal places. So that we'd round that to 0.837, right? 3 places. So it is likely it's very likely that they're going to approve the whole batch. That's a terrible method. All right, we are out of time. We are over time. Okay, so looking at number 16, in a study of helicopter usage and patient survival, among the 48,244, right there, here, let me do this, patients transported, 290 of them, what did they do? Left the treatment center against the medical advice, and the other 47,954 did not leave. If 40 of the subjects transported are randomly selected, what is the probability that none of them left the treatment center? Probably that none of them left the treatment center. Well, what's the probability that one did not leave? You're just going to grab one. Let's just start with 1. Well, what's the total? You know, the number that did not leave over the total, right? That's how we always do probability, the number of whatever you want over the total. So what's the number that did not leave? 47,954 over the total 48,244. So that's the probability that 1. If you're just saying, I'm just going to grab one patient, what's the chance I got somebody that didn't leave? It would be that fraction, right? This fraction, whatever that is, that would be for one person, because that's just grabbing one patient out of the total. Now, the question, what they're really saying is, what's the probability that none of them, none of what? None of the 40. What if you have, what's the probability that 40 did not leave? Well, what that really means is what? Oh, actually, let me hold up and say what I'm getting here. When I divided this fraction, I'm getting 0.993988888. Anyways, that's probably that 1 did not leave. So what's probably that 40 did not leave? Well, that's, like, what if they just asked 2? Let me just ask this question. What if they said, what's the probability that 2 in a row did not leave? Well, that'd be an and, wouldn't it? The first does not leave, and the second not leave, and they're going to 40, and the third does not leave, and the fourth, etc., right? This keeps on going. I messed up over here. And the fourth, ... So for 40 in a row to not leave, it's a big and. The first does not leave, and the second does not leave, and the third does not leave, and the fourth does not leave, etc. So that means you need to take this answer we just got up here, the answer right here that we got for 1, the 0.99398888, and you need to raise it to the 40th power and hit enter on your calculator, because and means multiply. So when you do 40th power, you're multiplying that number by itself 40 times. And here is the answer I got, 0.7857. That's the chance that 40 in a row did not leave. All right, let's go to the last question, number 17. Basically, they have a surge protector arranged in one line that's called series, in one straight line. The P and the Q are 2 surge protectors. assume that each surge protector has a 0.89 probability of working correctly. So P and Q in a straight line, or P and Q in what's called parallel configuration. Those are two different ways of setting up the surge protectors that would protect from the plug and the electricity shooting through and hitting your TV and wrecking your TV, or the plug and the electricity shooting through one of these two ways and hitting your TV and wrecking your TV. So how should you set up a surge protector, two surge protectors I mean, that would be the most helpful? So let's do part A here. If two surge protectors are arranged in series, that's this way, what's the probability that a voltage surge will not damage the television? What's probably that they'll do their job, and protect? Well, let's figure out this question. What's the probability that they will fail? Well, for them to fail, the P would have to fail and the Q. P fail and Q fail, right? For P would have to fail and Q would have to fail, right? Because if there's some kind of crazy electricity and P failed and Q failed and it gets on through to the TV, if both surge protectors P and Q fail, then the electricity will get through and wreck your TV. What's the chance that P is going to fail? Well, it says right here, oops, I bumped the button, right here, 0.89, right? The probability that it'll work, I'll just say, the probability that it works is 0.89. So then what's the probability that it fails? Well, 1 minus, remember, because opposite is always 1 minus. That'll be 0.11. So the chance that a surge protector is going to fail is 0.11. So the chance that P is going to fail, 0.11, and Q is going to fail times 0.11, right? So the probability that both will fail is 0.11 times 0.11. Remember, and is multiply. That's what we've been learning. And is multiply. And so what do I get? The chance they're both going to fail is 0.0121. 0.0121. That's the chance they're both going to fail. Now, that's not quite exactly what they asked me. They asked me what's the chance that they're going to work and not damage. So now, if they both fail, if both P and Q, if there's some kind of high power electric surge comes in here and P fails to stop it and Q fails to stop it, it'll get through and wreck your TV. So what's the chance of that? 0.0121. But the opposite, if either one of those is working, if either P or Q is working, they don't both have to work in the series configuration. If just P is working, it'll block the surge and it won't get to your TV. Or if P fails, if P is broken and fails, if Q is working, that'll block it from getting to your TV. So basically, if just one of them is working, so that's the opposite, isn't it? We would say the probability that they don't both fail. That's the opposite of the probability they both fail. So it's 1 minus. Remember, opposite is always 1 minus. So that would be 0.9879. That's the probability that they don't both fail, because it's the opposite of the chance they both fail. It's 1 minus it. So the answer to that part is 0.9879. That's the chance they don't both fail, because if they both fail, then the surge is going to hit the TV. What's the chance they both fail? 0.11 times 0.11, 0.0121. It's the chance they both fail. So the opposite of that, 1 minus that, is the chance they don't both fail. And so at least one of them works, and the surge is blocked. So see how I came up with that? I started by saying the chance that one surge works is 0.89. They gave me that. And then the chance that one surge fails is opposite. Opposite of working is failing. 1 minus that is 0.11. So then the chance they both fail, P and Q, is 0.11 times 0.11, 0.0121. That's the chance they both fail. And the chance they don't both fail, 1 minus that, 0.9879. Let's go to part B. So now part B is going to be a little different. It's asking us the same question, but it's asking for the parallel. If the two surges are in parallel, what's the probability that it will not damage? So now, what's the deal with parallel? We'll look at the parallel. If the surge comes in here, and it's crazy, now if it goes the way of P, it's basically going to try to go both ways, because it can, right? It's a parallel configuration. So what if P's working and blocks it, but Q is not? It'll get through and hurt your TV, won't it? You see the problem? They have to both be working to block it. This is not as good a configuration. They have to both be working. If either one of them is not working, it'll get through. That was different over here. Over here, if either one of them worked, they didn't have to both be working, just one had to work. But here on the parallel now, they have to both be working. So basically, what's the probability that the first works and the second works? Meaning P works and Q works. That's what you got to have, right? You got to have them both working to block it for it to work. Well, what's probably the first one works 0.89. That's the probably it works, and the other one 0.89. So it's 0.89 times 0.89, which comes out to be 0.7921. 0.7921 is the chance they're both working and thus block the surge to the TV. So that ends up coming out a lower chance they're both working than the last problem. Was a better chance because putting them in series was a better way to go. This is a better way to go, because if one of them is not working but the other is, it'll still block it, won't it? If P fails but Q is still working, it'll block it. But for the parallel setup, they have to both be blocking. If either one of them's not blocking, it'll get through. So that was a lower chance. That was 0.79% chance that way will block the surge, will work and protect your TV. And there's a 98% chance if you do it in series that it'll work and protect your TV. So which arrangement should be made for the better protection? For sure the series. It's this option, huh? Higher probability of protection. What does the other one say? Lower? Probably no, not lower. That's crazy. So it's right there. Higher probability.